This is Classical Physics 2, and we're doing chapter 24 problems. And before we start, we should do a review of things. So if I'm in series, that means I have one followed by another in series. My total resistance is going to be the sum of my individual resistors. My total voltage is going to be the sum of the individual voltage. My total power is going to be the sum of the individual powers. My total current is going to equal the individual currents. Whatever current I have going through one has to be going through each of them because I'm in series. My capacitance, total capacitance, follows a 1 over rule. 1 over capacitor 1 plus 1 over capacitor 2 plus 1 over capacitor 3. My inductance adds total inductance L1 plus L2 plus L3. That doesn't look like an L2. My conductance follows a 1 over rule. 1 over G total is 1 over G1 plus 1 over G2 plus 1 over G3. Did I leave anything out? My impedance, X of L, is going to add X of L1 plus X of L2, blah, blah, blah. And impedance as a capacitive thing, X of C1 plus X of C2. All right, now, if, on the other hand, I'm in parallel, assuming I spelled parallel right, then I'm going to do it with resistors, so I look like that. But in parallel, my resistance total is going to follow a 1 over rule. 1 over plus 1 over plus 1 over. My voltage is going to be the same, so it's going to be voltage 1, which is the same as voltage 2, which is the same as voltage 3. My power total is going to be the sum of the powers. My current total is going to be the sum of the individual currents. My conductance total, my capacitance total is going to be the sum of the individual capacitance. My inductance is going to follow a 1 over rule. My conductance is going to add my impedance is going to follow a 1 over total, 1 over X of I plus 1 over X of I, whatever, is going to follow a 1 over rule for both of them. In either case, if I have a loop, then the sum of the voltages across the loop has to be 0, and if I have a node, then the sum of the currents going into the node has to be 0. So those are just rules that are in the back of our head, and we may or may not use them depending on what the problem is. Okay, so we're going to start with problem number 6. I have an isolated capacitor of C1 carrying a charge of Q0. Its wires are then connected to a second capacitor of C2 previously uncharged, what charge will each carry? What will be the potential difference across each? Okay, so I've got capacitor C1, charge Q0, and then connected. Then it's connected to a second capacitor, previously uncharged. So the issue is, did I do this or did I do that? Which one did I do? So in this case, I only connected one end to the other capacitor. In this case, I connected two. So to be more correct to the problem, we connected it like that. So it's saying I'm connected these guys in parallel. All right, so first thing we have to understand is that the total charge is going to be conserved, will be conserved. So that means that Q0, the initial card, has to be Q1 plus Q2 when I hook them up. Because I'm in parallel, the voltage has to be the same. So V naught is going to be V1, is going to be V2. Whatever the voltage was originally is going to have to be, well, that's not totally true. But when I get done, the voltages have to be the same. V1 has to be V2 because I'm in parallel. Okay. So given that V1 has to be V2, we can rewrite that and say that Q1 over C1 is equal to Q2 over C2. And then we could go and say, well, if I go and take my total charge and I subtract away charge 1, then I've got Q2. That's going to have to be equal to over C2 as well. So those guys are all correct, and then I can solve for Q1. So I'm going to take that guy is equal to this guy and solve for Q1 and say Q1 is equal to Q naught C1 divided by C1 plus C2. Okay, did I skip enough steps doing that? Okay. And then I can go and say, well, what is Q2? Q2 has to be Q naught minus Q1. Alright, so that's be Q naught minus Q1. So I bring that on the other side of the equation, and okay, so that's going to be Q naught minus Q naught C1 over C2 plus C1. C2 plus C1. So I'm using that Q1 to replace him, and then I'm solving for Q2. So I've got that Q2 is equal to this, and I can find a common denominator and add those guys together and say Q2 is equal to Q naught C2 over C1 plus C2. Skipping enough steps to do that. And then I'm going to ask myself, what is the voltage? Well, V1 has to be V2, we know that. And V1 is Q1 over C1. And V2 has to be Q2 over C2. Q2 over C2, which would be Q naught C1 over C1 plus C2 divided by C1. And then I end up solving for V. Oh, I left too much out there. Then I end up with V being equal to Q divided by C1 plus C2. So I go and regroup that guy into that guy. All right. So that's problem number 6. Now we're doing problem number 10. Well, look at all these words. In a dynamic random access memory computer chip, each cell chiefly consists of a capacitor that charges, it has a storage charge. That's correct. Not only that, but I have to refresh it like 1,000 times a second too. Each of the cells represent a single binary bit of value 1. When it's a 35 microfarad capacitor, femtofarad, Fermi, is that Fermi? Farad? 10 to the minus 50 is charged to 1.5 volts, or 0 when it's uncharged. When it is fully charged, how many excess electrons are on the cell capacitor negative plate? Okay, so we got to do part B first. So we're looking for the electrons on the plate. So we're going to look at equation 24-1, which gives electrons at the plate. You can see that my charge is CV, and my charge is the number of electrons times E, which is going to be minus CV. So let my minus signs go away, and I find the number of electrons are going to be CV divided by E. Okay, well, my capacitance was 35 times 10 to the minus 15 farads, and my voltage was 1.5 volts, and my charge on an electron 1.60 times 10 to the minus 19 coulombs, and I end up with 3.281 times 10 to the 5th electrons. But I tell myself, I probably don't have that many significant digits, and I would be right. I only have 2 significant digits, so I'm going to call that 3.3 times 10 to the 5th electrons. So every single memory location, when it is a 1, has 330,000 excess electrons on its negative plate. B, after charge has been placed on the cell plate, it slowly leaks off at a constant rate of 0.30 times 10 to the minus 15 coulombs per second. How long will it take for the potential difference across the plate, across the capacitor, to decrease by 10% from a fully charged value? Oh, 1% from a fully charged value. Okay, well, first thing we'll do is decide that the charge is proportional to voltage. which means that if I have a 1% decrease in voltage, that means I'm going to have a 1% decrease in charge. All right, so my delta Q is 0.01 of my Q, and my delta T is going to be change in Q divided by change in Q, change in T. Alright, so I'm going to have a change of 0.01, and I'm going to divide that by the well, I'm not going to do that yet. So that's going to be 0.01 capacitance times voltage would be my Q, change in Q, change in T, and now I've got 0.01 times the capacitance, 35 10 to the minus 15th farads, 1.5 volts, divided by the rate of change, 0.30 10 to the minus 15th coulombs per second. And I end up with 1.75 seconds. But I look and I really only have two significant digits, so I'm going to call it 1.8 seconds is how long it's going to take me to discharge 1% of the voltage. All right, number 16. In an electric field, so I got an electric field of 4.8 times 10 to the 5th volts per meter, is desired, okay, an electric field of 4.8 is desired between two parallel plates. Okay, so I got two parallel plates, 1, 2, 5, and each of them have area 21.0 centimeters. And they're separated, the distance between them is 0.250 centimeters. What charge must be on the plates? Alright, well, we know that the voltage is equal to the electric field times D. So we know that, and we're going to use equations 24.1 and 24.2, and we're going to manipulate them a little bit and say that Q is equal to CV, which is going to be equal to epsilon naught A divided by D ED, which we're going to end up with epsilon naught area field. Okay, so now I know what epsilon naught is, I know the area, and I know the electric field, so now I can solve for Q. Okay, so Q is equal to epsilon naught 8.85 10 to the minus 12th farads per meter, and the area, and of course we want to be in meters, so 21 cubic square, 21 square centimeters is going to be 2.1 times 10 to the minus 4th meters, and then we have 8.8 times 10 to the 5th volts per meter, and we end up with the Q, the charge on the capacitor, has to be 8.92 times 10 to the minus 9th coulombs in order to have the electric field that I desire to have. Okay, I'm looking at number 24. Suppose 3 parallel plate capacitors whose plates have areas A1, A2, A3 are separated by D1, D2, D3 are connected in parallel. Thank you very much, author, for telling us that they're connected in parallel. Show using equation 24.2 that equation 24.3 is valid. All right, so I have 3 capacitors connected in parallel. I know that V1 is equal to V2 is equal to V3. The voltages all have to be the same. And I know that Q total has to be the Q1 plus Q2 plus Q3. I know that that has to be the case. And so this one has area 1 D1. This guy has area 2 D2. This has area 3 D3. All right, so Q1 has to be C1V because all the voltages are the same. So that'd be epsilon naught A1 over D1 V. And then I've got Q2 has to be C2V epsilon naught A2 over D2 V. And then Q3 would be C3 times the voltage epsilon naught A3 D3 voltage. And then I could go and say that the total Q total has to be Q1 plus Q2 plus Q3, so that'd be epsilon naught A1 D1 V plus epsilon naught A2 D2 V plus epsilon naught A3 D3 V. Then I could bring the voltage out and say that the capacitance total is equal to the voltage times epsilon naught A1 over D1, epsilon naught A2 over D2, epsilon naught A3 over D3. And then I could say, I could put the voltage on the other side of the equation, and I could have that Q total divided by V would be epsilon naught A1D, epsilon naught A2 over D2, epsilon naught A3 over D3. And then I could say, well, gee, Q total over V is just C total. So then I could go and rewrite that and say, well, C total is C1 plus C2 plus C3, and I am done. The next problem we're going to work is 32. Determine the equivalent voltage, the equivalent capacitance between the points A and B for the combination shown below. And then B, determine the charge on each capacitor and the voltage across each if the voltage A to B was V. Okay, so we draw a picture. Okay, so here's my point A, there's my point B, here's C1, C2, C3, C4. And the capacitors in parallel will add, so the combination of C1 and C2 would be C1 plus C2, and the combination of C3, C4 would be C3 plus C4. So now I've got two equivalent capacitance, call one C1, C2, the other one C3, C4. And now the combination of those two will follow a reciprocal rule. So 1 over the total, 1, 2, 3, 4, would be 1 over C1, 2 plus 1 over C3, 4. And if we find a common denominator and add together and then do a reciprocal thing of those, we'll find that C1, 2, 3, 4 is going to be C1 plus C2 times C3 plus C4 divided by C1 plus C2 plus C3 plus C4. And I only skipped a half page of steps there. You want me to put them back in? Oh, you're right. It's only a video. You can't answer me. Okay, well, I'll go and put them all back in. How's that? That'd be okay? We got enough time before lunch. Alright, so that being the case, C1, 2, 3, 4 is equal to C3, 4 plus C1, 2 divided by C1, 2 times C3, 4. Right? And then we can plug back in and say 1 over C1, 2. Well, we would invert. So we'll invert both sides. C1, 2, 3, 4 would be C1, 2, C3, 4 divided by C3, 4 plus C1, 2. And then we'd go back in and put in, let's see, 1, 2 is C1 plus C2, and C3, 4 is C3 plus C4. So we'd end up on top C1 plus C2 times C3 plus C4 divided by C1 plus C2 plus C3 plus C4, which is exactly what I had before, but now I've added in steps so that it looks sort of like I know what I'm doing. Okay, I promise not to do that in the next problem. Number 40. Okay, I've got some voltage across a network of capacitors. Oh, I'm not done with the last problem, am I? I still have to come up with, I came up with the total capacitance. Okay, that's fine. I came up with the total capacitance, 32. Determine the equivalent capacitance. Determine the charge on each capacitor and the voltage across each if we have the total voltage is V. Okay, so the voltage across C1, 2, so that combination is going to be 1/2 V. And the voltage across, well, it's going to be 1/2 V only if they're the same. All right. Okay, so now we're looking at part B, And we're going to go and do something weird. And let's see, Control V. Oh, there's part B. Oh yes. So now we can see that we take the charge across the total charge and the total resistance. We then break that up and we continue. And about 4 pages of work later, we end up with the voltage across each of the capacitors and the charge on each of the capacitors. And I could have done that sooner. Okay, good enough? Probably not. But good recovery. All right. Now we're going to look at problem number 40, where I'll do something just as sneaky and as devious I can imagine. Okay, so we have voltage V across A and B, and we've got 5 capacitors. And we want to determine, what do we want to determine? What is the equivalence capacitance? So I've got a point A, and I got a point B, and I've got 1, 2, 3 capacitors, and I've got another capacitor going that way, and I got another capacitor going this way. Okay, now it's just a matter of, can we label them properly? C1, C2, C3, C4, C5. Okay, so I got some in parallel, some in resistance. All right, well, part A. I'm thinking about this, and I'm thinking that better not show up on the test. All right, so anyway, I say, well, the total charge is going to be that equivalent resistance. So we have some voltage between A and B, so we better throw that in, times the voltage. Okay, and then I look at the picture and I say, well, that voltage has to be the voltage across C2 and C1. That voltage has to be the voltage across C5 and 4. That voltage has to be 2, 3, and 4. Okay, so we know that the V that's across this has to be V1 plus V2. The V across it has to be V2 plus V3 plus V4. The V across it has to be V4 plus V5. So that looks pretty good. We have all of 3 equations and 5 unknowns so far. Isn't that wonderful? All right. So that being the case, we also know that the total charge that the charge total has to equal Q, the charge across 2 plus the charge across 5. the charge total also has to equal the charge on 1 plus the charge on 3. And the charge that's on 4 has to equal the charge on 3 plus the charge on 5. Okay, so those are things that we need to know. So that being the case, the other things that we know is that the total capacitance times voltage is going to have to equal C2 CV2. The total capacitance times V also has to be C4V4 plus C1V1. And this is, I'm just redoing the Q's again. And C2V2 has to be C1V1 plus C3V3. Okay, so I'm going to rewrite these guys, and I'm going to have 6 equations. Okay, and they're going to be V is equal to V2 plus V1. V is equal to V2 plus V3 plus V4. V is equal to V5 plus V4. Q total, C total V is equal to C2V2 plus C5V5. C total V is equal to C4V4 plus C1V1, and C2V2 is equal to C1V1 plus C3V3. Now, what we'd like to say is that we have 6 equations, 6 unknowns, but it looks like we have more than that. But we have 6 equations, and when we have something like that, we know there's no way we're going to be able to solve those, right? We got to solve them simultaneously for C total. So I put them into Maple 11, which I happen to have a copy of. If you don't have a copy of that, they're only like $128 or so. And we get that the equivalent capacitance is C1, C2, C3 plus C1, C2, C4 plus C1, C3, C5 plus C1, C4, C5 plus, I'm running out of room, C2, C3, C4 plus C2, C4, C5 plus C3, C4, C5 divided by C1, C3 plus C1, C4 plus C1, C5 plus C2, C3 plus C3, C4 plus C3, C5 C2, C5 plus C3, C4 plus C3, C5. Isn't that lovely? All right. Now, that being the case, we can move on to part B. Clearly, without Maple, we'd be hard-pressed to solve that particular problem. The chances of us making an error are large. So we're in 40, and we're doing the B part. Determine the equivalent capacitance if C2 is equal to C4 is equal to 8 microfarads, and C1 is equal to C3 is equal to C5 is equal to 4.5 microfarads. Now, that seems like a reasonable thing to be doing. And so now it's just a matter of, rearranging our equation because so many things are the same. Okay, so if it's not too small a print, we can look at our equation and we can see that we're going to get 4 times C1 squared C2 plus 3 C1 C2 squared plus C1 cubed divided by 3 C1 squared plus 4 C1 C2 plus C2 squared. And now we put our numbers into that equation and we see that the total capacitance is going to be 6 microfarads. Yeah, we're going to believe that, all right. Okay, you don't believe me. I'll accept your disbelief. Okay, moving on to number 44. That was much too much fun. Number 44. A parallel capacitor has fixed charges of Q and minus Q. The separation of the plates is then tripled. By what factor does the stored energy in the electric field change, and how much work must be done to increase the separation from D to 3D? And the area of the plates is A. Oh, that's nice to know. Okay, so we have charge. Charge is constant. And we're going to go 3 times the distance. And which implies the capacitance is going to go down by a factor of 3. Down by, it's going to be 1/3 of what it used to be. Now, my energy that I start with is going to be the charge squared divided by 2 times the capacitance that I start with. And my energy I have stored when I end, I'm going to have the same charge, 2 times 1/3 the capacitance that I started with. Okay, and then we want to know how much did the stored energy change. So that'd be U2 divided by U1, Q squared 2C divided by Q squared to 1/3 C. Everything goes away and all I have is a 3 left over. So if I keep the same charge and I separate the distance of the plates by 3, then the energy being stored goes up by a factor of 3. All right, now, how much work was done? So B, how much work is done to store the energy? So U2 minus U1. So the work is going to be the difference in energy. So U1 unit is going to be 3U1 minus U1, which is going to be 2U1. Alright, so 2U1 is going to be 2 Q squared divided by 2C1. We know the capacitance, so that's going to be Q squared over epsilon naught area divided by D. And the D can go on top, and I can say Q squared D over epsilon naught area. So that's how much work was done to store the energy. Okay, I'm now looking at problem number 48. A capacitor is charged at 12 volts. It's disconnected from the battery, then connected to an uncharged 3.5 farad capacitor. Determine the total energy stored before the two capacitors are connected, after they're connected, and what is the change in the energy. Okay, so part A, we want energy. We're going to use the equation 24.5, and we want to find the energy stored, and I'm going to go with 1/2 C squared V naught squared, and I'm going to go 1/2 2.2 microfarads times 12 volts squared, and we're going to come up to how many significant digits are there in the problem? 3 significant digits. So we're going to leave our answer at 3 significant digits, 1.58 times 10 to the minus 4th joules. Okay, so that's how much is stored originally. Part B, the total charge available is going to be the initial charge, so total charge is going to be the same as the sum of the two charges. And because I'm connecting it across, I'm going to have a parallel combination. So C total is going to be C1 plus C2. So the energy stored when I connect it was totally 1/2 Q squared divided by C total, which is going to be 1/2 C1 squared V naught squared divided by C1 plus C2. Okay, so I'm going to put those numbers into my calculator and find that U2 is going to be 1/2 2.2 times 10 to the minus 6 farads squared, 12 volts squared divided by, I'm going to add them both together, 5.710 to the minus 6 farads. And I end up with 3 significant digits again. I end up with 6.11 times 10 to the minus 5th joules for my B answer. Now my C answer is the change in energy stored. So that'd be U2 minus U1, 6.11 10 to the minus 5 minus 1.58 10 to the minus 4 joules. So my change is going to be a minus 9.73 times 10 to the minus 5 joules. And that's going to be my change in energy. Okay, now I'm going to do number 56. How much energy would be stored in a capacitor of problem 43 if a mica electrolyte is placed between the capacitor, between the plates. Assume the mica is 1.3 millimeters thick and therefore fills the entire space. Okay. So we're going to go to problem 43, and we get that we have 420 microcoulombs is our charge, and we have that the distance, the dimensions of the problem are the same. So I've got square plates of 8 centimeters on a side, and the air gap is 1.3 millimeters, which is the same as the problem is. Okay, then we're going to use equation 24(5), and we're going to say that U is equal to 1/2 Q squared over C, which is 1/2 Q squared over K C naught, which is going to be 1/2 Q squared D over K epsilon naught A. Okay, so we're going to do all that. And then we're going to go look for the K. What is the K for mica? And we can find the K for mica is 7 on page 638. So we find that page 638. I find that K is equal to 7 because I have mica. Now I'm ready to solve the problem. U is equal to 1/2 420 10 to the minus 6 coulombs squared and distance 0.0013 meters divided by the 7 divided by epsilon naught divided by the area, which I turn from centimeters into meters squared, and I end up that my energy being how many significant digits? There's 2 significant digits, so I'm going to round my calculator down to 290 joules. Okay. Now look at number 64. The quantity of liquid available in a storage tank is often monitored by a capacitor sensor plate. In this case, we're monitoring liquid nitrogen. The sensor is vertically aligned cylinder capacitor with an outer and inner radius of RA and RB, whose length L spans the length of the tank. When a non-conducting liquid fills the tank of height H from the tank's bottom, the dielectric in the lower and upper regions between the cylinder capacitors is a liquid, K liquid, and so the dielectric is either K liquid or K vapor, respectively. Determine a formula for the factor of the tank filled by liquid in terms of the level sensor capacitance. Okay, so we're going to do that first. Alright. So we're going to consider figure 2430. No, 2433. Okay, so I'm looking at 2433. Okay, and I'm going to use the example 24.2. Example 24.2. And I'm going to say the capacitance is going to be the capacitance of the liquid plus the capacitance of the vapor part. Okay, and so that's going to be 2 pi epsilon naught K of the liquid H, some height, divided by the natural log of the inside diameter divided by the outside diameter, plus 2 pi epsilon naught K of the vapor times the total length minus the height H divided by natural log RA divided by RB. Okay. And okay, what are we supposed to be doing here? Determine a formula for the factor F of the filled tank by the liquid in terms of the level. Okay, so basically we want to know how far the tank is filled. So that would be some H over L. Okay, so what we want to do is we want to manipulate the equation, manipulate that equation up there in such a way that we can have an H and an L come out. Okay. So I'm going to take that equation and say I can bring a 2 pi epsilon naught H, 2 pi epsilon naught well, I can bring out a 2 pi epsilon naught divided by natural log RA over RB and if I do that I'm going to have K of the liquid H plus K of the vapor L minus H. And is going to be C. And then I'm going to want to manipulate that a little bit more and say, well, I can have that be 2 pi epsilon naught L over natural log RARB times K of the liquid minus K of the vapor times H over L plus K of the vapor. And that would be equal to C. And then I could bring out the H over L and say that H over L, which is my factor F that I'm looking for, is going to be 1 over K of the liquid minus K of the vapor times C natural log RA over RB divided by 2 pi epsilon naught L minus KV. Okay, well that looks good for the first one. Now we're going to have to do part B. By connecting a capacity measuring instrument to the level sensor, F can be monitored. Assume the sensor dimensions, there are sensor dimensions, blah, blah, blah. What value of C corresponds to the tank being completely filled and completely emptied? Okay, so the B problem. So full implies that H over L is equal to 1. Okay, so we're going to do the full guy first. So we're going to have 1 is equal to I think we'll go back. We're trying to solve for C. So we're going to go back to this equation. Going to go back to that equation where I've solved it for C and put in my numbers. Okay, so we'll go in copy that and move it down here. Don't you wish you could do that on your homework? C. Okay, so that's what we're going to do. So C is going to be 2 pi epsilon naught 8.85 10 to the minus 12 Coulomb squared Newton meter squared. Divided by natural log, and RA is 5 and RB is 4.5. Okay, 5 over 4.5, and the dimensions go away, so I don't have to change the dimensions to meters or anything. Times K of the liquid 1.4 minus 1.0 times 1 plus the K of the vapor, which is 1.0. Okay. And we put that in our calculator and we get the capacitance full is going to be 1.5 times 10 to the minus 9th farads. Okay, then we look at empty. Capacitance empty. And which implies that H is 0 and H over L is going to be 0. And I'm pretty sure I can grab that equation again. Yes, I can. The issue is that what I did There we go. That's good. I got it again. And now I'm going to find capacitance empty. Okay. That guy is going to be 0. Where's my L? 2 meters. Where is my 2 meters? Okay, so I needed 2.0 meters in there, which I'm sure that I had. Alright, so back to our equation again, and we're going to have 2 pi epsilon naught and we're going to have a 2. This is a 1, so it's going to be times 1 divided by a natural log of 5 divided by 4.5. And when we put that in my calculator, you get 1.1 times 10 to the minus 9th farads. So I better have a good instrument because that's not going to be very much. And that ends the EMPTY. That ends chapter 24 problems.